What is pressure? Pressure is the force distribution over an area, and it is defined as force over area, P equals F over A. To try to gain an intuitive understanding of what pressure is, I have a very silly example here of manatees over lizards. And we will use just qualitatively the relation P equals F over A to try to understand which of these two lizards is less unhappy. Obviously, they're both quite unhappy having manatees on top of them. Well, since we know that F is equal to ma in all cases, we can replace F with ma. The acceleration in this case is due to gravity. The manatee is accelerating due to gravity downward. So we can replace, in this case, A with G, and we can relate get the pressure for each one of these two lizards. Pressure 1, that is the pressure that lizard 1 on the left is experiencing, is equal to m1, the mass of manatee 1, times g over the area of that cylinder, the blue cylinder. On the right, we have P2, the pressure that lizard 2 is experiencing, is going to be equal to mass of manatee 2 times g divided by the area of that cone, the red cone, that little pointy part that the lizard is going to experience. Well, since the two masses are the same, because it's presumably the same manatee, maybe they're twins or something, we can just substitute m1 and m2 with m, just get rid of it, and get mg over a1 and mg over a2. Since we know that the area of a cylinder is larger than the area of the cone, the left lizard will experience a lower pressure than the right lizard, and therefore the lizard on the right will likely succumb to its injuries. Atmospheric pressure discusses the pressure due to the atmosphere. Well, the atmosphere itself is made up of air molecules from where you're sitting or standing all the way up to outer space, meaning that as you're walking around on your day-to-day life, you are carrying with you an invisible column of a bunch of air molecules above your head. How come you don't feel it? Well, luckily you've evolved not to. You would feel it if you were under different conditions. So if you're out in outer space or right at the edge of it, there would be significantly less air above your head. You would feel it. You would feel a lesser amount of pressure above you. And if you were inside of an ocean way, way deep, well, the column above your head would not just be air, it would be water too, and water being denser, you would feel significantly more pressure. And you may have experienced it when you dive into a pool, that you would feel more pressure above your head. That's the idea of atmospheric pressure. We don't feel it because we've evolved not to. Sort of like how we don't feel our clothes after a few minutes of wearing them. We just don't want to experience it. We don't need to. There's no reason to sense that. Well, at any rate, we can discuss what this means. Um, Instead of calculating this pressure, which we could do with force over area, and again, I can go to each one of these individual molecules, get the force that it experiences, that it exerts, divided by the area above my head, say for example, to try to get the atmospheric pressure. That's a pain. And you would, since air is moving around and shifting from place to place, and since you're moving around and shifting from place to place, calculating it becomes impractical. So instead of that, we use average values, and we call that the atmospheric pressure. And it would change depending on your elevation on Earth. If you're at sea level, you would experience more pressure than if you were up on a mountain, where the column of air, well, is now shorter. If you were inside of in a valley, your column of air would be, well, longer, and you would have more air molecules above your head, so the pressure due to the atmosphere would be higher in a valley than it would be on a mountain. The average value at sea level we define to be the 1 atm, atm being a unit of pressure. It is not the SI unit of pressure, but it is a unit of pressure nonetheless, and we normalized it by calling sea level atmospheric pressure to be 1. 1 atmosphere is the atmospheric pressure. Well, using other units like the bar or the Pascal or torr, you could see how that's related to 1 atm. 1 atm being equal to 1.01325 bar or 101.325 kilopascal, etc., etc. The SI unit for pressure is the PA, the Pascal. So 101,325 Pascal being the atmospheric pressure. That's the SI unit of atmospheric pressure. And it is defined as, well, let's go back and to our previous slide, and you could see that it is Newton per meter. How do we measure pressure? Well, we can use a device called a barometer, and you may have heard of that. And in a barometer, one uses mercury. And what happens is inside of this tube, you have a tube up there. The top of the tube is evacuated. There's nothing in it. It's a vacuum. And below that vacuum space, below that blue space, is mercury in gray. And this whole thing is submerged inside of a pool of mercury. Since the atmosphere is pushing down on the mercury in the pool, it will make this thing go up the tube, right? So imagine you're pushing your hand inside of water. You will make the water go up a tube if you put a tube in there. Well, that's figuring that. You can use that same idea to determine how much the atmosphere is pushing. Okay, why do we evacuate that tube? Well, if we didn't evacuate the tube, then the pressure inside the tube and the pressure outside the tube would be the same, and they would push with the same pressure and nothing would go up. So we evacuate the tube. We suck everything out using a vacuum or something, and then we stick it in, and then the mercury will go up. Why do we use mercury? Well, mercury is denser than water. We could use water, but then if we use water, then we have to have a significantly taller column, which is not practical. Using mercury allows us to have quite a short column, and very practical to uh, to build and use. About a foot. No, sorry, about 3 feet. Um, and we can also use this other device called a manometer to determine the pressure of an unknown gas. And we will revisit this in a minute. Okay, again, the pressure unit, the SI unit, will be the Pascal. It is defined as a Newton per meter squared. Okay, we've seen these other units when we just showed the atmospheric pressure, so we can relate the Pascal to a bar, to an ATM, to a PSI, or to a torr. Torr is the same as millimeters of mercury, which we just saw in the previous slide. The millimeters of mercury is an easy and convenient way to measure atmospheric pressure. And it just so happens that mercury rises 760 millimeters due to atmospheric pressure. And that's the unit that we use for pressure, using millimeters of mercury. You may have also heard in weather forecasts people use inches of mercury. Similar idea, instead of measuring in millimeters, one can measure in millimeters, in inches, and get about 30 inches. So that's how one converts from one to the other. The US customary system, the unit one uses for pressure is the PSI, which is pound per square inch. All right. In fluids, and fluids being either gases or liquids, it's harder to define a mass, right? Because it flows, right? If I'm looking at water, if I grab water, if I drew a square around some area of water, that's nice, but it doesn't, it's hard to measure that mass. How do I do that? Well, instead of using a mass and trying to weigh it, one uses volume. Much easier for me to define a volume inside of a water bottle or an ocean or the atmosphere or something. And since we know density is mass over volume, well then mass is equal to density times volume. Okay, so how does that help me? I know the pressure is force over area, always. For fluids, it's harder to use force over area. So let me replace force with, well, mg, and replace m with rho v. So In On the right side, rho Vg is basically mg over A. But instead of mass, I'm using rho times the volume. Okay, now I have a V over A in that fraction. So what's V over A from a unit analysis? Volume is length times width times height, and area is length times width. If I divide them out, I get that volume over area is just height. So I can replace V over G with H. And I get that pressure for fluids, much easier for me to measure, is rho GH, the density of the fluid, the gravity, and then height. Height is easy to measure for fluid. I just take a ruler and I measure the height. So I can use that to find the pressure for fluid. Instead of trying to get a mass and weigh it and figure out what area I'm using, I can just take a height of a liquid or a gas, and I can find what pressure it exerts. All right, let's discuss gauge pressure and absolute pressure. Well, absolute pressure is what we've just discussed all along. All these pressures I just told you about, they were absolute. An absolute unit means that there is no negative. Zero is zero. Zero pressure means there's no force exerting anything. And that makes sense. 0 inches means there's no length. So that's what I mean by absolute pressure. It's the actual pressure that you're measuring. Right now in the room you're sitting, it's likely 1 atm. Unless you're up in a mountain or something, it's likely about 1 atm of pressure. Okay, and gauge pressure is something we're going to be used as a comparative tool. So we're going to take the actual pressure in the room and subtract the atmospheric pressure to get this thing called gauge pressure. So assuming that the room you're in is about 1 atm, then the gauge pressure in the room you're in is 0. Right? So the pressure is actually 1, but we would call the gauge pressure 0. What does that give you? It gives you a comparative sense. It compares the pressure in a chamber, in a room, in a vessel, wherever, to that of the atmospheric pressure. And if it is less than the atmospheric pressure, then the gauge pressure will be negative. And that's what you may have heard people say, negative pressure. There is no such thing as negative pressure. Pressure is well, zero pressure is zero force. But there's a negative gauge pressure, which is a relative pressure. So a negative pressure would mean that something is getting sucked in. So maybe inside of an air cabin on an airplane, or inside of a fume hood in a chemistry lab, you would feel suction coming in there because, well, the pressure inside of those two chambers is less than that of the atmospheric pressure. So things go into the lower pressure. That's what we mean by negative pressure. If you have a pressurized vessel, which one needs in various environments, say on a submarine, then the gauge pressure will be higher than 0. Okay, going back to the manometer, one last little thing. A manometer is a device that I can use to measure the relative pressure of something I don't know. So in yellow on the left side is pressures that I don't know, of some gas there or some liquid that I don't know. And on the right side is the atmospheric pressure. It's basically a tug of war. In blue, I have mercury. And what happens is the green pushes on the right, the yellow pushes on the left, and whichever one pushes with more force goes down further. So in this particular example, the yellow pressure is higher than the green pressure because it pushed the mercury further down. Maybe in other cases, yellow and green are the same, in which case the levels of the blue would be the same on either side. And maybe in some other cases, the green is stronger than the yellow, in which case this would be an inverted picture. And on the right, you would see a lower level than on the left. At any rate, this is a very easy and convenient way to measure pressure, and people use this all over the place because it's so convenient. Of course, with an electrical signal, but this particular way to measure pressure is really sublime. So people use this all over the place. Well, what I'm going to say is that the pressure on the left side and the pressure on the right side will be, well, equal for this to occur, because right now this thing is stable. So on the left side, I have the pressure of this gas, the yellow gas, plus the pressure of the mercury on the left side. On the right side, I have the pressure of the atmosphere pushing down and the pressure of the mercury pushing down. And those two things are equal. Well, the pressure of the gas and the pressure of the atmospheric pressure, I'm going to leave them as P. And PATM I can look up. P of the gas is what I'm going to solve for usually. Well, what's the mercury? Mercury being a liquid, I'm going to replace that with rho GH rather than using force over area. So I'll do that. For liquids, I know that P is equal to rho GH, replacing both of those. Pressure on the left side would be P gas plus rho GH left is equal to P ATM plus rho GH on the right. And rho is the density of mercury, G is 9.81, and PATM I can look up. And the height, well, I can measure it. See, in this particular case, the relative height I can see is about 11, whatever unit it is. On the right, it's 11 higher than on the left. So I could call the left 0 and the right 11. And using the appropriate unit, I mean, I would want to use SI unit, I could find the pressure of the gas. And lastly, since height is below, in general, one uses a negative.